Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Now, in the last few lectures we have been discussing about transition metal olefin complexes. We have looked into their bonding, their preparations as well as reactivity aspects of these very important class of organometallic compounds. We have seen as to how these compounds are important from catalytic perspective, because they are important intermediates in many catalytic reactions. We have discussed that also. We have also looked at the bonding scenario that exists between olefin and the transition metal in the transition metal olefin complexes. So, we in the last few lectures what we have seen is we have looked into details of transition metal olefin complexes from all perspectives, right from synthesis, bonding, structure and reactivity as well as characterization of these complexes. Now, in this lecture we are going to start another new class of organometallic compounds. These are mainly transition metal diolefin complexes. Now, one may think that what is the need for studying transition metal diolefin complexes. Once we have studied transition metal olefin complexes, the reason being simple is that there is a difference in properties of transition metal diolefin complexes as opposed to simple transition metal olefin complexes. This difference not only is reflected in the bonding as well as the reactivity thing, but also in the other preparations and other aspects of it. So, there is a definitive need for studying transition metal diolefin complexes, despite having spent quite a few lectures on transition metal olefin complexes. For example, this diolefin can be of two types. That means that it can be isolated diolefins, for example, where these two olefinic bonds are not in conjugation of each other, or it can be conjugated diolefins. Where these two olefinic bonds are in conjugation of each other. So, what it turns out that unconjugated or isolated diolefins resemble more closely the unconjugated monoolefin complexes, more closely resemble monoolefin complexes. So, when these two olefinic bonds are not conjugated, they sort of resembles the monoolefin complexes which are somewhere over here. On the other hand, when this olefinic is conjugated, as a result of conjugation, they have different scenario, and that needs to be treated separately, and hence the reason for studying these diolefin complexes. So, these have delocalized pi MOs, pi molecular orbitals with various energies and symmetries with various energies and symmetries such that they require different treatment. Now, with that being in mind, we are going to focus on some of these types of ligand in the this part of the lecture, where we are going to look at how does conjugated diolefins interact with the transition metal. And with that being apart, let us take a look at this simple example of a conjugated diolefin, which is just butadiene. So, to begin with, let us sort of take a look at the molecular orbital structure of a metal butadiene complex, as is represented by this formulation Tm dash butadiene. And let us take a look at the ligand orbitals. And as well as the corresponding metal orbitals that interacts with them. Now, so there are 4 p orbitals of the type shown over here, where all the bondings are in one phase, and this is a sigma type orbital and represented by psi 1. Since butadiene has 4 p orbital, linear combination will give 4 frontier fragment molecular orbital FMOs, and that would react with the corresponding atomic orbital of the metal. So, this is the combination where it is bonding on one side, all the 4 are in same phase. So, that is psi 1. The other possibility is that it would have one node, this had no node, all has same phase. The other possibility is that it has one node, that means that it is one phase in the top, another phase at the bottom. This is a psi 2 and this is a pi type orbital. The third combination can be where it is same phase at the back and opposite in the front, and this is denoted as psi 3 and also is a pi type orbital. And the last combination is where it is antibonding in nature, and it has opposite phase, and this is also designated as psi 4, and it is a sigma type orbital. Now, this gives a idea as to how these butadiene orbitals are located. So, you have psi 1 when all 4 are bonding and in sync, then you have one with next has one node, and then you have the other one where it is plus minus minus plus, and then you have plus minus 4 orbitals, of which 2 first and the last one are sigma type, and the second one and the third one are pi type, and we let us see how they interact with the metal orbitals. The metal orbitals involved s orbital, for example. So, this is a s orbital or proper symmetry can interact with this psi 1, or p z orbital So, this is p z or a d z square orbital, which is the z square orbital. Similarly, for this psi 2, the corresponding metal orbital which can interact with psi 2 are that is p y orbital, as well as d y z orbital. So, which is d y z orbital. As for the psi 3, the orbitals which can interact is p x orbital, which is p x orbital, and that is given by that, or d x z orbital, Now, as for the antibonding orbital, which is psi 4, the metal orbital that can interact is d y x, which is given by and this is d x y. So, what it does is it gives an idea as to which ligand orbital interacts with what kind of metal orbital. So, what we see is the metal orbital that interacts with a particular ligand orbital has same phases to interact with. For example, it is black at the bottom, this is all black, or this can top is black, it can go up there, and the z square also is this. Now, over here where there is one mode, the metal orbitals which can interact has the similar thing, white and black as similar to that, or white and black as similar to this. This is a d orbital, this is a p orbital. So, orbital of appropriate symmetry come and match, and the same applies to these orbital. So, frontier molecular orbital of the ligand puts a restriction on the metal orbital that can interact with these elements, with these metals, and can provide an insight as to what kind of interactions this can go through. In this butadiene binding, then one can see that psi 1 or the first interaction is sigma donating interaction, where psi 1 to metal sigma bond is happening, which is a sigma interaction. Now, psi 2 to metal is a pi kind of ligand to metal interaction. And the third one is metal to psi 3 pi kind of interaction. Now, this is reverse, metal is donating, and psi 4 is metal it is a delta interaction, metal to this a delta interaction. Now, so this is kind of a side on interaction, where these lobe, all 4 lobes are interacting with all 4. So, this is a delta kind of interactions, and these sort of tells what kind of bonds, if at all this interaction would form, what kind of bonds they would form. This says that the first one would be a sigma, these two a pi, and that one a delta bond. Also, one must note that these bears some more significance. For example, both psi 2 to m, this interaction, as well as m to psi 3 interactions, okay, these two would these two psi 2 to m or m to psi 3 interaction. So, these two would result in lengthening of terminal C bonds. That means, these two side bonds would be lengthened, and shortening of internal C bonds. So, what is interesting is that predominance of these two interaction would ensure that these terminal CC bonds are lengthened, and in contrast the internal CC bonds are shortened. And that is a very interesting observation that has emerged out of this frontal molecular orbital diagram. And we are going to see the implications of this in bit more details, particularly when we look at the energy diagrams of all these 4 molecular orbitals. So, the electronic excitation, for example, the electronic excitation of free butadiene induces changes in bond lengths comparable to the one that we have just discussed. Let us sort of illustrate this as follows. For example, there are butadiene orbital, this is let us say the energy, and there are 4 butadiene orbital which are psi 1, psi 2, psi 3 and psi 4, of which 2 of them, there are 4 electrons. So, 2 of them are populated, and that would sort of give the butadiene fragments to be something like that, or so the bond distance of the internal CC bond is much longer, about 145 picometer, whereas the one with double bond character is much shorter, about 136 picometer. Now, when the butadiene is excited, one of the electron is excited to a higher orbital, then again we have these 4 energy states, and what we see that one of the frontier electron which is over here gets excited to psi 3. Now, what has happened is the psi 3 which had a population of similar phase, that gets populated. So, to understand that, let us sort of look at psi 2 and psi 3. Psi 2 is this is psi 2, and when it gets excited, let us take a look at the structure of psi 3. Structure of psi 3, which is the internal double bond is double bond in character. So, this is a bond order of that is increased, this is something like that, and indeed now the internal bond has decreased and it has become 139 picometer, whereas the external one is now 145 picometer. So, as a result, what one observes is that lengthening of terminal CC bonds as well as shortening of internal CC bonds. So, that is a interesting observation that we see that electronic excitation of free butadiene would lead to shortening of internal bonds and lengthening of terminal bonds, and the same thing can be also be seen when the butadiene coordinates to metal. There also we see that depopulation of psi 2 and population of psi 3 would result in analogous lengthening of terminal bonds and shortening of CC bonds. So, with this let me conclude today's lecture, which was diolefin complexes. We began the lecture by looking at how is the diolefinic complexes different from olefin simple monoolefinic complexes. We have also looked at the bonding scenario of olefinic complexes, how that this molecular orbital interacts with that of the fragment molecular orbital, and how that leads to change in the bond lengths of the internal as well as terminal CC bond lengths of the diolefinic ligands, and that provided a very useful insight as to we see that the impact of the metal coordination to conjugated diolefin or as well as the excitation, light excitation of the free diolefin have similar effects. So, with that let me conclude today's lecture on diolefinic complexes. We are going to take this a bit more and a few other examples or few other new types of organometallic complexes in the next lecture. Till then, goodbye, and I look forward to seeing you in the next lecture. Thank you.